Hi, so today we're going to discuss flat mirrors, spherical mirrors, and images formed by refraction and thin lenses. So in this video, we will discuss how images are formed as a result of reflection and refraction when light interacts with mirrors or lenses. So we will first discuss flat mirrors. So the flat mirror is the simplest kind of mirror. Okay, so let's consider this mirror here, and suppose a point source of light is placed at the point O, where this point source of light represents the object. Okay, so we can consider the light reflected from the object as the source of light, and a single point on an extended object as a point source of light. Okay, so let the distance between the object and the mirror be p. Then light rays leaving the object are reflected by the mirror, and they diverge upon reflection, as you can see here. Okay. So if we draw dashed lines as extensions of these reflected diverging rays, all the dashed lines will meet at the point I, right? So to a viewer here, the diverging rays appear to be coming from the point I, behind the mirror. So point I is the image of O, of the object O, okay? This is a general way of locating an image, okay, which is by extending diverging rays to the point where they meet and intersect each other, okay. So the distance q behind the mirror represents the position of the image, and so q is known as the image distance. So images are classified as either real or virtual. So a real image is formed when light rays pass through the image point and diverge from it, okay? And a virtual image is formed when light rays do not pass through the image point, but the extension of the light rays diverge from that point. So the image of an object in a flat mirror, as you can see, is always virtual, okay? So let's consider the figure here, which is known as a ray diagram, and it is a method used to study mirrors and lenses. So in a ray diagram, just a few numbers of the many rays that leave a point source are drawn, okay? And then the location of the image is found using the laws of reflection and refraction. And then geometry is used to solve the problem mathematically, okay? So this method is known as a ray diagram. So for this diagram here, let's consider the tip of the gray arrow. So the arrow is the object. And let's consider two rays of light reflecting from the mirror. So we consider, of the many rays leaving, we consider only a few, which is only these two rays. So one is this and the other one is this. So one ray, this one, takes the path PQ to the mirror, and then it reflects back to itself. So the second ray takes the oblique path PR, as you can see, and reflects back at the same angle of incidence according to the law of reflection. So this is the second ray path. And if we extend the two reflected rays, this reflected ray and this one, if we extend them, they will meet at this point here, P dash, which is the point where the rays appear to diverge from, right? So repeating this process for points other than P on the object will construct a full image of the arrow to the right of the mirror, right? So using geometry, you can see that the triangles PQR and P dash QR are identical. So PQ is equal to P dash Q, or P is equal to Q. And we used the absolute value of Q here because there can be a positive or negative sign associated with it, as you will see in the next section, okay? So we conclude that the image distance in front of a flat mirror is at the same distance as the object is in front of the mirror, right? So both object and image are at the same distance from the flat mirror. Also, the geometric model here shows that the height h dash of the image is equal to the object's height h. And we define the lateral magnification m equal to image height over object height, which is equal to h dash over h, right? And this is the general definition of magnification for any type of image, okay? And in this case, for a flat mirror, m is equal to 1 because h dash is equal to h. And also note here that the image is upright, right? Because the image arrow is pointing in the same direction as the object's arrow. And this upright image is indicated by the positive sign of the magnification value. And we will see later that an inverted image with a negative sign of the magnification can be formed. Also note here that the flat mirror appears to have a left-right reversal, right? Because when one raised the right hand, the image appears to raise its left hand, right? But the reversal is not left-right, but it is actually front-back reversal. So to understand this, suppose you hold a fork in front of the mirror, as you can see here. You will see that in both the actual fork and its mirror image, the head of the fork is to the left and its tail is to the right, in both the actual fork and the mirror image. And so the mirror does not affect the left and right axis. Also, suppose you hold the fork in the vertical direction in front of the mirror and let the head of the fork points downwards and its tail is in the upward position. Then for both the fork and its mirror image, the head is down and the tail is up. So the mirror does not affect the up-down axis either, right? But now suppose you hold the fork perpendicular to the mirror with its head pointing toward you. So the actual fork has its head in the front side and the tail in the back, right? But as you can see, the mirror image of the fork has its front-back axis flipped. So you're looking at this actual fork from its front, but you're looking at its image here from behind it, right? So the apparent left-right reversal is actually front-back reversal, and it is caused by the light rays moving toward the mirror and reflecting back. So suppose you raise your right hand in front of the mirror. Notice how the thumbs of both your hand and this image are on the left side. So there is no left-right reversal here, right? It is the front-back reversal that makes the image of the right hand appear as a left hand. So as an example, let's consider two flat perpendicular mirrors and we place an object at the point O. So as you can see, three images are formed, I1, I2, and I3. And to find the location of each image, we use this ray diagram and draw dashed lines as extensions of the diverging reflected rays. So as you can see, these are the reflected rays, and we extend the reflected rays and they meet at I1 and I2 and I3, okay? So you can see that the image I1 is the image of the object in mirror 1, right? And it is a result of extending the yellow and green rays. And they meet at I1. And also I2 is the image of the object in mirror 2. Okay, and we can find it from extending these purple reflected rays. And I3 is formed. And I3 is actually the image of I1 in mirror 2. So it is the image of I1 in mirror 2. So I1 serves as the object of I3. Or equivalently, we can say it is the image of I2 in mirror 1, right? So the image of I1 or the image of the image I1 or the image I2 can be considered as the object of I3. Okay, so I3 is a result of the rays reflecting twice after leaving the object O. So we will now discuss images formed by a curved mirror, either the concave surface of the mirror or the convex surface, okay? So let's first consider concave mirrors. So a spherical mirror is named spherical because its shape is a segment of a sphere, as you can see here. So this figure here shows a cross-section of the spherical mirror, okay? So as you can see, light is reflected from the inner surface here, and that is why it is known as a concave mirror, okay? So the radius of curvature of the mirror is R, and its center of curvature is C. And point V here is located at the center of the spherical segment. And the line passing through C and V is known as the principal axis of the mirror, okay? So suppose a point source of light is placed at O on the principal axis to the right of C. So as you can see, we consider two diverging rays from O, this ray and this ray, and after these rays reflect from the mirror, they meet at the point I, which is the image point. And then they continue to diverge from I as if I is a source of light. So an observer will see light diverging from I, which is the image, right? So this image is a real image because the light rays pass through the image point, okay? Unlike a virtual image in the case of a flat mirror where the actual light rays do not pass through the image point, but only their extensions. So we will use a simplification model in which we assume all rays diverging from the object to make small angles with the principal axis, such as these rays here. And such rays are known as Paraxel rays, and this is known as the Paraxel Approximation, because these rays always converge and pass through the image point I after reflection, okay? But if we have rays that make large angles with the principal axis, they will converge at points other than I, and therefore they produce a blurry image, okay? So let's consider now this ray diagram here to find the image distance Q by knowing the object distance P and also knowing the radius of curvature R, and also we want to find the magnification factor of the image. So we consider V here as the reference point from which we measure the distances of the object, image, or center of curvature. So the figure shows two of the many rays leaving the object, right? So the first ray here passes through C and hits the mirror here perpendicular to the mirror surface and is then reflected back to itself, right? And the second ray here strikes the mirror at V and is reflected back at the same angle of incidence according to the law of reflection, okay? So the image of the tip point here of the arrow is at the point here where the two rays intersect each other, right? So let's consider the two right triangles shown, this triangle and this triangle here. So using the first triangle, this big one here, you can see that tan theta is equal to h over p, so h over p. And using the small triangle here, you can see that tan theta is equal to minus h dash over q. and the negative sign indicates that the image is inverted. So h dash is a negative number. And so the magnification factor m is equal to h dash over h, and we substitute from these two equations, and we get minus q over p. And also, if we use this right triangle here and this small right triangle here, we can see that tan alpha is equal to h over p minus r. So this distance is p minus r, and also is equal to minus h dash over r minus q. And if we equate them and we substitute for h dash over h, we get this equation, and it gives 1 over p plus 1 over q is equal to 2 over r, and this is known as the mirror equation. And it applies only in the Paraxel ray simplification model, okay? So if the object is very far from the mirror, so if p is large compared to r and approaches infinity, then 1 over p approaches 0, and this equation gives q approximately equal to r over 2, which means that when the object is very far from the mirror, then the image point is halfway between the center of curvature c and the center of the mirror v, okay? So as you can see from this figure here, only the rays that are traveling parallel to the axis coming from the distant object, only those rays strike the mirror, because other rays that are not parallel to the axis miss the mirror, okay? So the point at which these parallel rays intersect, this point here, after reflecting from the mirror, is known as the focal point F. And it is at a distance f known as the focal length from the mirror, okay? And f is equal to r over 2. So we can write the mirror equation as 1 over p plus 1 over q is equal to 1 over f, okay? We will now discuss convex mirrors. So the figure here shows image formation by a convex mirror. So in this case, light is reflected from the outer convex surface, okay? So it is also known as a diverging mirror, because as you can see, rays diverge after reflection as if they are coming from a point behind the mirror. So the image formed in this case is virtual, because the light rays do not pass through the image point. Let's take the image point here as the head of the arrow. So as you can see, the actual light rays do not pass through the image point, and that is why it is virtual. So only the dashed lines, the extensions of the light rays, pass through the image point. And also, as you can see, the image is upright and is smaller than the object. So the equations we derived for a concave spherical mirror can be used for a convex mirror by changing the signs of the variables. So let's consider the region at which light rays originate as here as the front or real side of the mirror, and the other side here as the back or virtual side. And as you can see, this is the front and back side for a concave mirror, okay? And the table here shows the sign conventions in terms of where the location of the object or the image is located, whether it's in the front or back side. So as you can see, P here is positive if it is located at the front side of the mirror, and negative if it's located at the back side, and same goes for Q. And the height h dash of the image is positive if it is upright image, and negative if it's inverted. And the focal length and the radius of curvature are positive for a concave mirror and negative for a convex mirror, and the magnification is positive for an upright image and negative for an inverted image, okay? So here I included a ray diagram for the case of a concave mirror as an additional example of how to use a ray diagram. So in general, only two rays are necessary to locate an image, but here we choose a third ray for clarification. So as you can see, all three rays, they originate from the same point on the object, which is the top of the arrow, but you can construct the image of any other point on the object the same way, okay? So the first ray is parallel to the principal axis and is reflected through the focal point. The second ray here originates as if it is coming from the focal point here, right? And it is reflected parallel to the principal axis. This second ray, in the case, it is as if it's coming from the focal point in the case of the object distance being less than the focal point. But if the object distance is greater than the focal point, so this is the object, this is, for example, this is the focal point, let's say the focal point is here, then the second ray would pass through the focal point and then reflect it parallel to the principal axis, okay? But we are including just this example here, okay? So the third ray here, so it originates as if it is coming from the center of curvature for the case of P less than F, or passing through the center of curvature as this ray here. A similar ray is this one, passing through the center of curvature if the object distance P is greater than F, okay? And it reflects back to itself, as this case here. This ray, it reflects back to itself, okay? So for a concave mirror, the real inverted image formed here, this is a real inverted image because the image is at the front side of the mirror, and it is so it is real image and it is inverted. This image moves to the left as the object comes closer to the mirror. So when the object is closer to the mirror, as in the case here, between the focal point and the mirror, the image is virtual and upright, okay? So it's virtual because it is located at the back side of the mirror, okay? It is larger than the object. So this example of a concave mirror here is used in a makeup mirror or a shaving mirror because the face will be the face, which is the object, will be located between the focal point of the mirror and the mirror itself, okay? So the image will be magnified and upright. So if you move away from this mirror, so this is the shaving mirror and this is the object, so this is the face. If it moves away from the mirror, so at a distance larger than the focal point, then the image will be inverted, as in this case, okay? But if the object is here at the focal point, then the image will be indistinct because it is infinitely far away, and you can check this using the mirror equation, okay? And the convex mirror, like this one here, is used in stores at high positions because it can cover a large field of view of the store, and it makes it appear smaller in the mirror. So let's consider an example here. So suppose we have a spherical concave mirror of focal length of 10 centimeters, and we want to find the location, magnification, and orientation of the image of an object located at different distances from the mirror, okay? So because the mirror is concave, then the focal length is positive, so it's plus 10 centimeters. So in the first case, the distance of the object P is 27 centimeters, so it is larger than the focal length F. So we expect the image to be real and inverted, as in this case here. So at the front side, it's real and it's inverted, okay? So we find Q from this equation to be 15.8, and the magnification, which is minus Q over P, equal about minus 0.6, okay? So as you can see, the absolute value of m is less than 1. So it means that the image is smaller than the object, okay? Also, the negative sign of m indicates that the image is inverted. And because q is positive, it means that the image is located at the front or real side of the mirror. So the image is real, okay, as we have discussed in this table here. So now suppose that the object is at a distance of 10 centimeters, which is at the focal length of the mirror. So then q is equal to infinity. If we substitute, it's equal to infinity, and this means that the image is formed at an infinite distance from the mirror, which means that the reflected rays do not converge, but they are parallel to each other after reflection. So now suppose the object is at a distance of 6 centimeters from the mirror, then q is equal to minus 15 centimeters, and m, which is minus q over p, is minus minus, so it's plus 2.5, which means that the image is magnified, okay? And it is upright because m is positive. And the negative value of q indicates that the image is virtual, which means it is located at the back side of the mirror as expected, right? It's so the distance of the object, 6 centimeters, is less than the focal point, which is 10 centimeters, and this is it's describing a similar situation here. The image is upright, it's virtual, and it's magnified. So we will now consider images formed by refraction at the surface of a transparent material, and we will apply Snell's law of refraction and the Paraxel approximation, okay? So let's consider two transparent media of index of refraction n1 and n2, where the boundary is a spherical surface of radius of curvature of r, okay? So suppose the object is placed at O. As you can see here, the Paraxel rays are refracted. So they are refracted by the spherical surface, and they converge at the point I, which is the image point. So let's consider a single ray leaving O, this ray, and from Snell's law you can see that n1 sine theta 1 is equal to n2 sine theta 2 here. And if we consider only Paraxel rays, we can assume that sine theta is almost equal to theta, and n1 theta 1 is equal to n2 theta 2. So we will now use geometry for the analysis. So consider the triangles OPC and PIC. So we have theta 1 is equal to alpha plus beta, and here we use the fact that an exterior angle theta 1 of any triangle is equal to the sum of the two opposite interior angles alpha and beta, okay? And in a similar way, beta is equal to theta 2 plus gamma, okay? And then we substitute for theta 1 and theta 2 in this equation, and we get this equation. And in this small angle approximation, we have tan alpha is almost equal to alpha, and same goes for beta and gamma, and this is equal to d over p, and tan beta is equal to d over r, and tan gamma is equal to d over q, okay? And then so we substitute in this equation, and we get this equation here. So this expression shows that all Paraxel rays leaving an object at a distance p from the refracting surface will be focused at a distance q, okay, which is at the back side of the surface. So the magnification is minus n1q over n2p, and you can show this using a geometric model, but I'm not going to include it here. So note here how a real image is formed at the opposite side from which light originates. So the image here is real because actual light rays pass through the image point, so it's not a virtual image, okay? So for spherical refracting surfaces, the table here shows the sign convention, and you can see it's the first line is similar to the case of the mirror. So P is positive when the object is at the front side and negative if it's at the back side. But Q has opposite signs to the case of the mirror. So Q is actually positive and the image is real if the image is located at the back side. And Q is negative and the image is virtual if it's located at the front side. So this is opposite to the case of the mirror here. Okay. And H dash is positive if the image is upright, negative if it's inverted, and R is positive if the center of curvature is at the back side, and negative if it's at the front side. So we will now discuss flat refracting surfaces. So in this case, R here goes to infinity and this goes to 0, and then we have this equation, which gives this equation here, and this shows that the sign of Q is opposite to P, right? And so the image formed by a flat refracting surface is on the same side of the surface as the object. So as you can see here, the object and the image are both at the front side, and this is the back side. So the at the front side, Q here is negative and the image is virtual, and it's at the front side, okay? So the figure here shows that because N1 is greater than N2, then the refracted rays deviate away from the normal, as you can see, right? And also this equation here shows that Q is always smaller than P if N1 is greater than N2, right? And this means that the image of the object in a medium of a high refractive index is closer to the flat surface than the object itself, right? As you can see, the image is closer to this flat surface than the object when viewed from the lower refractive index medium, right? And that is why an object under the surface of water will appear closer to the surface than it actually is when viewed from above the water, okay? And this is why if you look at a fish swimming from above, it will appear closer to the surface than it actually is, right? This is the refracting surface. We can consider the water here as this flat refracting surface, right? So this is the object, the fish, and the image of the fish will appear closer to the surface somewhere here, okay? So we will now discuss thin lenses. So a thin lens is a piece of glass or plastic that has two surfaces, either a segment of a sphere like this one, or a plane like this one, okay? And they are used in cameras, telescopes, and microscopes, and they form images by refraction. So the figure here shows cross sections of thin lenses. So it shows two groups. So the first group, this one, is thicker at the center than the rim, and they are known as converging lenses. And the other group is thinner at the center than the rim, and they are known as diverging lenses, okay? So consider the figures here, which shows the focal length of the different lenses. And note that the focal length is defined as the image distance that corresponds to an object at an infinite distance. So in the first example here, rays that are parallel to the principal axis coming from an object at an infinite distance, they pass through the focal point here after being refracted and converged by the lens, right? So the distance from the focal point to the lens is known as the focal length, okay, f. Also, note here that we will use a simplification model known as the thin lens approximation, where the thickness of the lens is assumed to be negligible. So a thin lens has one focal length and two focal points, which corresponds to parallel rays traveling from left to right. So if they are traveling from here, from an object at an infinite distance, they will converge here. And if the object is here and the rays are coming from here, they will converge here, okay? And for the lens shown here, you can see that so these are the parallel rays coming from an object at an infinite distance. You can see that they diverge upon refraction from the lens, right? And the focal point here, in this case, is defined as the point from which the diverging rays appear to originate. So this is why these lenses are known as converging lenses, because the parallel rays, they converge after passing through the lens, right? So they converge like this. And these lenses are known as diverging lenses because the parallel rays, they diverge after passing through the lens, as you can see here. So they diverge, okay? So suppose we have an object placed at a distance p from a converging thin lens, as you can see here. So the figure here shows the ray diagram, and we are showing three rays leaving one point at the tip of the arrow here, okay? But note that the point of intersection of any two rays is enough to locate the image, but we are using three rays here for clarification. So the first ray, this one here, passes through the center of the lens, okay? So it passes through the center, it continues along a straight line. The second ray, this one, is parallel to the principal axis of the lens, which is the horizontal axis passing through the center of the lens. And after refraction, as you can see, it passes through the focal point, okay? And the third ray, this one here, passes through the focal point, and it emerges parallel to the principal axis, okay? And all of these rays, they meet here at this point, and the point here where these rays intersect is the image point, and it is at a distance q from the lens. So let's consider these two triangles, this triangle here and this triangle here. So as you can see, the tangent of the angle alpha is h over p, and it's also equal to minus h dash over q. And so the magnification h dash over h is equal to minus q over p. So as you can see, this equation for the magnification of the lens is the same as that for the mirror, okay? And also we have tan theta is equal to d over f, and it's also equal to minus h dash over q minus f. This distance here is q minus f. And we have also d equal to h, and we substitute. So we equate these two equations, we substitute for d as h, and then we use the magnification equation, and we finally get this equation here. So this equation is known as the thin lens equation, which is identical to the mirror equation, and it can be used with either a converging or a diverging lens by using the appropriate sign convention, okay? So as in the case of mirrors, the side from which light approaches is known as the front side of the lens, okay? And so converging lens under this convention has a positive focal length, and the diverging lens has a negative focal length, okay? Also, if we know the radius of curvature of the front surface of the lens, R1, and the back surface R2, then the focal length of the lens in air is related to R1 and R2 and to the index of refraction N of the lens through this relation. So this equation is known as the lens maker's equation. So we will now consider two additional ray diagrams which are used to locate the image. So the first one here shows a converging lens, and the object in this case is located at a distance p from the lens that is less than the focal length, okay? So unlike this case here where the object is located at a distance p greater than the focal length, okay? So three rays are shown here for clarification. So the first ray, this one, is parallel to the principal axis, and after being refracted, it passes through the focal point at the backside of the lens. Okay, and the second ray here, this one, is drawn as if it is coming from the focal point here, right? For this case of P less than F, so this ray here is similar to this ray that passes through the focal point for P greater than F, and then it emerges parallel to the principal axis as this ray has its extension passing through the focal length and emerges parallel to the principal axis. So the third ray here passes through the center of the lens and continues in a straight line. So for this diverging lens here, the first ray is parallel to the principal axis, and after being refracted, it diverges where its extension passes through the focal point. And the second ray, this one here, is directed towards the focal point, so its extension passes through the focal point and then it emerges parallel to the principal axis. And the third ray here passes through the center of the lens, and it continues in a straight line. So as you can see, the point of intersection of these three refracted rays here, they can be used to locate the image, okay? So as you can see, for a converging lens, if the object O is at a distance p greater than the focal length, then the image is real and inverted at the backside of the lens. Because as you can see, the sign convention here, Q is positive and the image is real if it's located at the backside. The image is virtual if it's located at the front side. So for this case here of a converging lens, when the object O is located at a distance p less than the focal length, then the image is virtual because it's at the front side, so it's virtual, upright, and it's magnified. And this is the case of a magnifying glass where it creates a magnified image of an object, okay? So for this case of a diverging lens, this is the object here, and as you can see, the image is virtual at the front side, so it's virtual and upright for all object locations. And such lens is used in a peephole of a door to give a wide angle view, because as you can see here, it creates a small image of a wide field of view. So let's consider this example of a converging lens of a focal length of 10 centimeters, and we want to find the location, magnification, and orientation of the image for each case of the object's distance. So the first case, the object is at a distance of 25 centimeters, which is greater than the focal length. So we can find Q using the lens equation, and it's equal to 16.7 centimeters, and the magnification is minus 0.667. So the positive sign of Q shows that the image is real at the back side of the lens, and the magnification, it indicates that the image is smaller than the object, and the negative sign of the magnification shows that the image is inverted, as expected, right? Because P is greater than the focal length. The second case is that the object is placed at the focal length of 10 centimeters, and Q in that case goes to infinity, which shows that the image is formed at an infinite distance from the lens when the object is placed at the focal point. So this means that the rays travel parallel to one another after refraction. So now suppose the object is at a distance of 6 centimeters from the lens, so it's less than the focal length. Then Q is equal to minus 15 centimeters and M is plus 2.5. So the negative sign of Q shows that the image is virtual, located at the front side of the lens, which, as we said, is the side from which the light originates, right? Also, the image is enlarged, and the positive sign of M shows that the image is upright. So let's consider an example of a combination of two thin lenses. So in this case, the image of the first lens, I1, can be treated as the object of the second lens, okay? And the image of the second lens, I2, is the final image that we get from the system. And suppose that the image of the first lens, I1, here, is located on the back side of the second lens. So here, not here like in this case, this is the front side of the second lens. So suppose I1 is located at the back side of the second lens, then the image is considered as a virtual object for the second lens, okay? Which means that P2, the distance of the object from the second lens, will be negative. So this is the case in this table here, backside virtual object. Then P is negative, okay? Also, the overall magnification of a system of thin lenses equals the product of the magnification of the individual separate lenses, okay? And also note here that this method that we will show can be used for a system of 3 or more lenses. So let's consider these two lenses here with a focal length of f1 of 10 centimeters and f2 of 20 centimeters, and they are separated by a distance of 20 centimeters. And suppose an object is placed at a distance of 30 centimeters from the first lens. Okay, and we want to find the position at magnification and orientation of the final image formed by the system. So as we discussed before, for a converging lens like this one, in which the object is placed at a distance p greater than the focal length, like in this case at 30 centimeters from the lens, the image formed is real and it's at the back side of the lens and it is inverted. So this is I1 here. So it's at the back side of the first lens, it's inverted and it's real because actual light rays pass through the image point, okay? So, and note here that, so these are the light rays that converge to the image point here of I1. They do not stop there, but they will continue. And as they continue, they are refracted by the second lens, okay? So this image I1 now is considered as the object of the second lens, okay? So let's calculate the location of this image I1 formed by the first lens, so Q1. So 1 over Q1 is equal to 1 over F minus 1 over P1. So 1 over 10 minus 1 over 30, and we get Q1 equal to plus 15 centimeters, and the magnification by the first lens for I1 is minus 0.5. So because I1 now is the object of the second lens, then this object I1 is at a distance of 20 minus 15, which is 5 centimeters here. This is 5 centimeters here from the second lens, okay? So P2 is equal to 5 centimeters. Then we substitute to find the location of the image formed by the second lens, Q2, which is equal to minus 6.67 centimeters, which shows that the image of the second lens is at the front side, right? According to this sign conventions, if it's negative, it's at the front side, it's a virtual image, right? here. So, and this is expected because the object I1 is at a distance less than the focal point, right, of the second lens. So from here we can calculate the magnification of the second lens, and the total magnification due to the two lens system is equal to minus the multiplication of M1, M2 equal to minus 0.667, okay? So the negative sign of the total magnification shows that the final image is inverted, as you can see here. I2 is inverted with respect to the initial object, right? And also because the absolute value of M here is less than 1, then the final image is smaller than the object, okay? So in the following, I included some additional solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.